Okay, so next speaker is Ribeiro from Lisbon, from the Instituto Técnico, and we'll talk about voltage-driven phases of quantum matter.
So I have this grandiose talk of voltage-driven phases of quantum matter, and I'm trying to convey some of how to work on this. So these are the collaborators. So there's a PhD student that just graduated, postdoc that is now in the US, and two senior collaborators, both in one in China and one in Taiwan.
Could you speak louder?
Okay, I'll try to speak louder. Okay, so this is my motivation slide. In classical dynamics, you know that non-equilibrium conditions plus nonlinearity gives you a very complex phenomenon. So here you have the Rayleigh-Bernard convection when you have two differences of temperature, and you can go from it's just diffusive transport to this convection rules. But I mean, you have it in many complex systems, including biological systems, where you can have self-organization and pattern formation. So now I want to pass from the classical to the quantum, and we have to simplify the problem. So let's first look at quantum, non-equilibrium quantum systems without interactions. This is the typical transport experiments. The kind of systems I'll be interested about is steady states of biased systems. So in a classical transport, you have two reservoirs, some constriction in the middle, and you can study transport. And so people know by now what happens. So if you have a clean system, typically you have holistic transport. And if you start to put impurities, depends on the dimensionality, but you can have diffusion or localization that turns the system into an insult. And you also have topological properties. Now, once you start to put interactions, things get a bit more complicated. And what you can do is hydrodynamics or generalized thermodynamics in this room. So, by the way, I apologize. I wanted to put a lot of reference here. So if you're not referenced there and you think you should be, you're in good company. Sorry for that. The issue here is that I really want to go to low temperatures, and because I want to connect to the equilibrium. So in equilibrium, if you have low temperatures plus quantum systems plus interactions, you have an ordered state, typically charged magnetic or superconductors. And so what I want to ask is that what happens to this ordered state once you put it between two reservoirs at different chemical temperatures. And I go to, I mean, in principle, you can have also different temperatures. I want to put temperature to 0 in both reservoirs. And the question I want to ask in general is that what will happen to this ordered state when you start to increase the voltage? So this is the overall. But before going to the interacting state, let me track back. So what are the possible scenarios you can have in this system? So first, you can have a system that is gapped. So the local, your system that you're trying to bias is gapped. And so there's an energy scale in your system, and nothing should happen until some energy scale. And after that scale, you break down the order some way. So this is your system that is robust, and then you break it. And kind of questions is how do I break it? What is this phase transition that is broken by this non-equilibrium drive? And you can ask, what is the state that I get afterwards? Another possibility is you have a gapless system. There's no intrinsic scale, so whatever you do, you will affect the system in some way. And you can ask, I mean, if the state is ordered, you can ask how the order will be formed, and is it stable or not? And if not, what is the new state? Okay, so now this is the slide I wanted. So before I look at the ordered state, let me look at the system without any interactions. So the kind of system I'm talking about, let's think about on a 1D thermodynamic chain between two reservoirs. Again, I'm going to low temperatures. So if you want, you can think about linearizing the dispersion relation around the Fermi surface. And if you have voltage across the system and this is current, I really am interested in this featureless transport regime where you don't explore mainly the edges of the. So this will change because at some point I'm going to make it the voltage. But the featureless non-equilibrium state I want to describe here, you can think about that in this linearized way. So, I mean, there's several ways of thinking about this, and maybe the easiest one is Landauer. So you have two leads at infinity, you send, I mean, there's some interface between the system and the leads, and you send some electrons, and they get reflected and transmitted. And in this picture where you linearize, this is the kind of distribution function of n of k as a function of k. So for equilibrium, this would be just some non-zero, 1 and then 0. Okay. And then out of equilibrium, what you get is this double step distribution. And so here the width of the step is related to the voltage you apply. And the height here, in this case of ballistic transport, relates with the way you couple to the reservoir. So by changing the way you couple to reservoir, you can change these heights.
Sorry.
Yeah.
So what do the blue and red curves?
Oh, this is for different temperature. Okay, temperature. I mean, here is rounded high temperature, and then you get sharp edges. Yeah.
For the voltage 0, the current is 0, right?
Sorry.
For 0 voltage, the current is
Yes. So this 0 is here. Okay, so now you can ask, well, let's characterize the state, and so this, again, 0 temperature. This state has sorry, finite temperature. This state has the correlation functions are decaying exponentially with some correlation lengths that diverge at 0 temperature. And at 0 temperature, it's still a power law as in equilibrium. And you can ask, well, now what is the phenomenon entropy? Because this is no longer pure state. If you take a piece of the system, you'll have a part that is proportional to the volume, but this is just because it's a mixture. It's no longer pure state. And then you have log corrections. So if these log corrections could appear if you have, could appear without the volume term if you do mutual information between two sectors. So this is, so these log corrections will have the 1/3 characteristic of the equilibrium state. So if you take delta to 0, this part will still remain. So delta is proportional to the voltage.
What is that?
Sorry, that voltage over Fermi velocity. And then you have some corrections, and these corrections depend on these heights of the jump that you have in this distribution. And you can compute them, and there's some function of the jump. Yes.
So if I look back at the picture of the N of K,
yeah.
So at finite temperature, this jump will be smooth.
Yes. You don't have the log. The log term is only at 0.
Because I mean, I have a paper where we compute the same setup, but using Limblad, some improved version of Limblad. And one funny thing that we discovered that even at high finite temperature there is, but maybe it's an artifact of the Limblad.
But if you have a discontinuity here, I thought there was some paper that has a discontinuity at 0. Is that one?
No, I mean, within this Limblad that we have, even at finite temperature, there is some discontinuity. But,
I mean, to have logs, you have to have discontinuities in the.
Yeah, indeed.
Okay, so then if you have.
Okay, so it would be nice to understand what's the difference in the work.
So so that's the source of the log is discontinuity.
Yeah.
But then you have some corrections to this central charge. I mean, in the because of So this is actually quite non-analytic. So if you compute this, so if you do numerically what you expect here as a function of voltage, you see that this thing is goes to a constant for time higher system sizes, and then there at v equals 0 it jumps to 1/3. That's what it should be. So it's really a non voltage. Okay, so now this is what I want to not categorize the non
Yeah, I missed the problem. How do you implement the voltage? Is it
Kelvin. I mean, it's just,
are you driving with Limblad at the boundaries or what?
no, it's really oh, sorry, spoiling my presentation. This is really a reservoir. I mean, a true zero reservoir in the sense that you integrated out an infinite.
So those are fermions.
Those are fermions.
Okay, so you have two fermionic reservoirs.
Two non-interacting fermionic reservoirs at finite at 0 temperature and finite chemical, and you change.
So maybe the question of Andrea, which is also related to mine, is what is the interaction between the path and the chain?
It's just a hopping.
Hopping.
I mean, I didn't go to this wide band approximation for the.
But it's
for the
quadratic
path,
in the fact.
but everything's quadratic.
Okay.
Here everything's quadratic. Okay, so what I want to tell you about is well, there's two models where I elaborate on quadratic fermions, and then one where I actually put interactions. And I mean, I want to tell you a bit more about this one, but you'll see that there's some brutal approximations. Okay. So first about the first model. So the first model is an example of this gap state that I told you about. So what we did is we take XY spin chain at the Ising Ising point. Now you can think about this in the spin or in the fermionic system. So you look at your chemical potentials like now are magnetic potentials, let's say, and you look at the order parameter of the Ising case. So in equilibrium, so the ordered phase. So if you compute this correlation function, this thing goes to phi square, and phi square is the order parameter. And then in disordered phase, you have something that goes exponential. So now I'm going to place myself at that point there. So 0h and gamma equals 1. And I'm going to change the magnetic potentials of those leads. So this is what you get. So this is the order parameter. So magnetic potential of one lead, magnetic potential of the other lead. This is equilibrium, and this is the ordered state. Now, if you look at this from the Bogolubov quasi-particles of the non-interacting spin chain, this is what you see here. So there are two bands, and what you're changing is the chemical potential. But remember that these are you're in the Majorana chain, right? You're in the Majorana chain, so these are not really charge is not conserved here. But still, there's a chemical potential, and this chemical potential. Well, things change as you move the chemical potential across the bands. So what does change? So in equilibrium, you're in the ordered state, and you keep in the ordered state. So you compute this correlation function, and you can get phi. So you keep there as long as the chemical potentials are inside this band, and then after that, they don't change. The order parameter doesn't change as long as you're inside the band, and afterwards you have a abrupt transition to a disordered system. You can say, okay, this is a first order transition. Nothing really happens in my system, except that if you compute how the correlation length behaves as you approach the ordered state, you'll see that it diverges at that point. So it's a funny transition where you have a discontinuous order parameter with the divergent correlation length. So we call, I mean, this is a mixed order transition. This is not the term we invented, and people have looked at this in the context of some classical models with longer range interactions, but they are a bit fine-tuned. So here you see some this mixed order transition in the context of a non-equilibrium system. Okay, so this is the example of some free model that is gapped. So now let me give you the other example, so the gapless case. So again, something you can map into free fermions. And this is hardcore bosonic chain. So again, hardcore bosonic chain, 2 chemical potentials, 0 temperature. So the ordered phase is this quasi-long range ordered system, right? Where correlation functions go as a power law with the exponent -1. And you ask, so what happens to this system when you put it up? And so this is the form of the correlation function that as soon as you put some voltage, decays exponentially with system size. So you kill right away the quasi long range order of the system. But you still get power loss, and you also get a shift. So if you see this in a momentum space, so if you compute the n of k of the bosons, which is the non-trivial quantity here, you see that the equilibrium would be something that diverges. I mean, it's here. It's the vehicle. It diverges as 1 over square root of k. And now as you increase the voltage, so first it doesn't diverge anymore, and then you get a shift. This is just that you have a finite current, so you have a current of bosons, so n of k will be shifted and no longer diverges. And so you can compute, because you can make free fermions, you can compute all these quantities as a function of these step sizes of the n of k for the fermions. And so you can also play with this power law, compute this power law as a function of the same quantities. And maybe what I want to remark here is that, again, this is very non-analytic limit, because so if you take v to 0, so if you say I have this non-equilibrium setup, I set v finite, and now I'll take it to 0 very slowly. So I'll see here. So if I take it to 0 very slowly, I can, so the imaginary part of the, so you see, as long as v is positive, this thing does not depend on v. So it's the same, so it jumps at v equals 0. So if you take it to 0 very slowly, you can realize this quasi long range order with very strange power laws, because the correlation lengths will go to 0 because this one depends on v, but then this power law will not. Okay, how much do I have?
7 minutes.
7 minutes. Okay. So now I want to go to the hard one. So this one is so I really want to put interactions in the two cases. So I want to take spinous fermions plus nearest neighbor interactions, something that also is gapped in the large U limit. So this is just a charge density wave order. I want to crank up the chemical potential and see how do I kill this ordered state. Okay, so now let me look at the phase diagram as U. So U is the correction, V is the voltage. So let me tell you about the limits that we know. So we know the equilibrium one. So this is Latinger liquid until U equals 2, and then it's a charge density wave, it's a gapped orbit state. Now, if I take U to 0 and I just change V, so this is non-interacting system. So what happens in the non-interacting system is the following. So these are my leads, and this is the bandwidth of the chain in the middle of the leads. So when I start to increase the voltage, I start to have current passing from one side to the other through the by using the electrons that are inside this region, the chemical potential difference region. As I start to increase the voltage, I start to get a larger and larger current, so the differential conductance is positive. But at some point, I saturate the amount of current that I can pass through the system, because you see my chemical potential are here and the bandwidth of the system is there. And so this is what happens here at G is 0, because I increase the voltage and nothing happens to the current. I'm passing the highest current I can. So this is the V. Another limit that we know is the Markovian limit, V equals to infinity. V equals to infinity is a limit that was studied by many people. I mean, this is that's even an exact solution by Thomas Rosen. So this one is also funny. It's so for small u and infinite voltage. Right now I'm in infinite voltage. I have a system that, if I look at the charge, I mean, here it's in spin, but this is the charge. The charge profile is something happens near one of the boundaries of the system, then the charge is flat. The distribution of charge is flat, and then something drops again in the other boundary. So this is the uniform charge distribution with ballistic transport. And then if you increase, so there's a phase transition to another phase where the charge distribution has a step. So here is 1 and here is 0. So because the voltage drop is infinite, so you fill half of the chain and you empty the other half, and there's a sharp transition. And this system is an insulator. Okay, so I'll give you a picture why this is the case. Okay, so and then there's this region that I would like to know how to tackle, but I don't really know. So what we did was mean field. Okay, so this is a mean field calculation. So let's try to. So what was the mean field? So you take these systems. So we know that I mean it's the charge that will be the main player here. So you just decouple this in charge, and then you do self-consistent. I mean the same thing I did before, but self-consistently for the charge. Since you have the boundary, leads, we have to do it space dependent. So it's really you have to do it in real space. So okay, so we compute the density of electrons self-consistently in real space in the presence of the bias, and then you compute the susceptibilities in R. So what do we know about mean fields? So it's, I mean, mean field gives you a transition right away at finite at 0u. Right? This is the mean field. It's actually, if you look at the order parameter as a function of u, it's exponentially suppressed here. So if you look at if you ever looked at the phase diagram of this thing for small u, not so different from the qualitatively from the true phase transition. So it's exact here, and it's qualitatively correct at infinite voltage, but it gives you the wrong value of the critical. So now I'm going to try to explore different limits. So let me first look at the strong coupling limit. And in the strong coupling limit, as I showed you before, a charge distribution that is a step. So in that case, you can simplify your model and then ask for a mean field solution that is constant here, then abruptly changes this constant there. And this will be my order parameter, this step order parameter. We call it a charge density step. So this is the Markovian insulator that was there by Tomasz. And this is the charge density wave. So this is the kind of order that you have. So you have this Markovian insulator, this charge density step insulator. Then you have a charge density step that is conducting, and the disordered state. This is if you don't allow for this charge density wave at pi. And let me just tell you what you have here. So this is the current. So the current, if you are in this state, rises, and then in this phase here, you have a current that decreases as you increase the voltage, and then it's 0 here and there. So let me give you just a mean field picture of why this happens. So as I told you, this is a step function here of the charge distribution, and so your chemical potential in one side and on the other side of the chain gets renormalized, and so you can see that the two bands. I mean, if you separate your system in two bands, let's say two chains, these two chains will have different temperature. Different chemical potentials or charging potentials, let's say. And so as you increase the voltage, you're doing two things. You're putting electrons in this window where you can conduct, but you're also increasing the relative energy shift of the two bands. So at some point, there's no band overlap, so you cannot pass electrons to one place to the other because there's no electrons to on the other side at that energy to pass. I will skip this one and just tell you about the full phase diagram that you can get. So I think for the large U regime, I think we get a good picture of what happens, but the mean field is much more iffy at smaller u. And at smaller u, we find a very nice phase, which is a charge density wave with the ordered parameter that depends on the voltage. So with the Q that depends on the voltage. And we can actually link this to the nesting conditions that are V dependent. But of course, so for large V, we think we are correct. At strong club, this also makes sense. But this phase is much more iffy because, I mean, mean field has clear. And so I will leave you with my last slide, which I hope this mean field phase diagram is sufficiently provocative to some more investigations in the field, hopefully with more controlled methods. Thank you.
So related to my previous one. So if you take this the N of K, and then I mean, at finite temperature, the discontinuity becomes smoothened. What happens if you at the same time you lower the interaction between the path and the chain? Does the discontinuity is restored, or
at finite temperature you always have
always smooth?
So I'm assuming that you have the same temperature in both reservoirs.
Okay, but if you put an imbalance in temperature,
I think if you put an imbalance in temperature, you have a discontinuity at 0. I mean, that is very
but there is a discontinuity, so you would have a log of neutral information.
Yes, because of this discontinuity is at 0.
Okay.
But the solution of frozen for infinite bias isn't also infinite temperature.
You don't care because you took the infinite bias first, so it really you don't care about. I mean, it's really. I mean, you can map it exactly to that. I think you.
I mean, because the leads are just fully filled.
Yes.
There's no temperature.
Yes.
Sorry, I forgot. What does the voltage mean in the Ising case?
I think it's some magnetization. So you have a Lagrange multiplier of your reservoir, which is the magnetization of the reservoir. I mean, but that you map in the free fermion case, it's just in the chemical potential of the fermion.
But I thought Mariana fermions don't have a conserved charge, so what does it mean?
Yes. So there's no conserved charge. Okay, a good point. So so actually, my reservoirs are here. Actually along this line, because this would be the and the system is there. So the reservoirs are gapless reservoirs at a potential that I choose. And the system is there. So there's no conserved magnetization, but there's a conservation of energy. So you can compute the current, the energy current. This one is well defined, but the magnetization is not conserved.
So is it like with your discontinuous thing, is it like at some point the voltage is enough or the bias is enough to start to inject domain walls?
Yeah, I think you can see it like that.
Is there some classical limit to this transition?
Classical image.
S equal 3.
Yeah. I don't know.
Okay. Thanks a lot, Pedro. And start again tomorrow at 9:30. But if you come early, there is a breakfast.